All right, dude, we are live. What's up, guys? This is Dem Keys, and today we're going to continue um, doing ESP32 stuff with Rust. We're going to continue learning about the ESP32 itself, and let's see where today's stream takes us. The plan so far is to uh, focus on two things. One is potentiometers, and the other is ADC, the analog to digital converter. So first, I want to learn how potentiometers work exactly. More specifically, I want to understand the voltage divider concept because potentiometers have three legs, and through those three legs, you're able to set up a voltage divider type of circuit. But I don't understand how voltage dividers are meant to work. So I wanna understand that first. I wanna understand the calculations surrounding it, and then I wanna proceed with trying to use a potentiometer to send in different types of values to the ADC in the ESP32. So I want to try and use the ADC to read different types of values coming in from the potentiometer. What else? What else was I gonna talk about? I actually didn't get too much done yesterday in terms of doing potentiometer research. I got busy doing something else, but we will try to make progress with POTS and ADC today. I have maybe an hour and hopefully 45 minutes. If not, um, if not an hour and 45 minutes, then definitely an hour and a half I'm gonna have for streaming. So within this hour and a half, let's try to make some progress. Let's try and learn something. Yesterday, I what all did we do yesterday? We played around with the potentiometer. I showed you the specific type of potentiometer which I have, which is a trim pot. I haven't set up my other potentiometer, the actual like the knob style potentiometer. I haven't. I didn't get the chance to do soldering practice, so I haven't set anything up with that. Dude, I'm kind of wondering if I should do a soldering stream as well, though it'll be incredibly hard to stream the soldering because there's a lot going on there. I have to concentrate on that specific thing as much as possible, and I cannot really, how do I say this? It's not the most convenient thing to try and make sure that the camera is able to see what I'm doing. I need to be able to see what I'm doing, and I need to be able to concentrate on what I'm doing. And there's a lot of there's there's a lot that can go wrong there, and that's why I'm not too sure about doing the soldering on stream. Once I'm comfortable with it, because I'm nowhere near what I would call good at soldering. I'm nowhere near even adequate, even average at soldering. I'm still very much a beginner. I still make a lot of mistakes. I need to get this down to a proper workflow. I need to get this down to like a workflow where I know for sure that what I'm doing is going to work. It shouldn't be like, oh, okay, I need to solder this thing. I'm going to try and hope that it works out. The first thing that I've noticed is that I don't seem to get the temperature right. I also need to look into if at all it's possible that my my soldering tips might be low quality, and because of that, maybe uh, they might be causing some issues with heat transfer. I'm not sure. That shouldn't be the case. I don't think so. It's still possible though, but I don't know. I don't think that's the case. You know, I was actually considering whether I want to buy copper tips because the place where I was buying these tips from, I specifically went with these. Um, I don't know what tips these are. They're silver colored tips, but I don't know what the specific material is called, what the specific metal is called. I bought that. It's just the regular soldering tips. Um, but they also had copper tips, and I was considering getting those. But then I was like, okay, let me first use these tips, which are, used more commonly, just in case I run into any issues or something. Like, let me first become good at soldering, and then I'll go for like special tips because copper, at least from my understanding, it's gonna transfer heat much quicker and much better as well. So I didn't want there to be situations where, because I'm a beginner, so the tips that I'm following or the info that I'm following for a different material of soldering tip, I try to apply that to the copper soldering tip, and then there's some kind of confusion for me. Okay, so yeah, like I was saying, um, I want to know what I'm doing when it comes to soldering. I want to be confident with soldering. That's the best way to say what I'm trying to say. I wanna be good at soldering. I wanna know how to solder. I don't want to just hope that, you know, the solder melts and the solder transfers and stuff. I want to know that yes, the solder is gonna transfer. And if it's not transferring, then I need to know what exactly the issue is so I can fix the issue. One issue is definitely that, the tip is not hot enough. That's one possible issue. Another issue is that it has become too hot and apparently the surface has oxidized, and that's why it's not transferring heat very well. Because I've noticed this thing in the videos that I've seen. They touch the solder to the tip, and instantly the thing melts. Whereas in my case, I would have to I would have to give it at least a second before, or maybe half a second, or let's say a second, before the solder actually melts. So that told me that there's some issue with heat going on. And in this case, it turned out that the heat was way too high. And so any flux that I was putting onto it, it wasn't really helping because the surface would get oxidized very quickly. And there was this other thing that I wanted to understand, which was Gemini was telling me that when the tip is really hot and you touch it to, let's say, the leg of a potentiometer, the heat transfers very quickly. And so then your iron isn't hot anymore, or your tip isn't hot anymore. I need to understand how that whole heat transfer mechanism is working. But yeah, this is what I'm saying this is what I mean when I say that I want to get this workflow down to an exact deterministic workflow. I want to get it down to a science. I want to understand exactly what's going on, and not just, hope that whatever I'm doing works. Because once I get better at soldering, there's so many things that I need to solder. There's so many modules that I haven't used yet because I haven't soldered them. There's actually ESP32s as well, ESP32 C3 Super Mini, for example. that I haven't used until now, solely because I didn't solder the headers onto it. There's a bunch of different modules that I haven't touched so far because they didn't come with the the headers soldered onto them, and I wasn't comfortable enough with soldering at the time. To be fair, not comfortable completely yet, but I'm getting there. I'm getting there. I'm also wondering if I should continue using the knife tip, or if I should try using the, I forgot what the other one is called, hoof tip. The hoof tip is basically like, imagine the hoof of like a I don't know, a horse or a moose or something. Imagine the shape of that. That's basically it. It's like a slanted kind of thing. Uh, the tip itself is basically a slanted flat surface. It's a flat surface that has been put at an angle, and that's your tip. So you have, because well, it's not exactly a flat surface. It's a little bit curved, but the the point there is that it's a larger surface area, and so it helps with different types of soldering. What was I saying? Where was I going with this? I forgot where I was going with this. Oh yeah, I'm wondering if I should try switching to the hoof tip. But then, with the amount of good things that I've heard about knife tips, I feel like I wanna get better at using the knife tip itself, because the knife tip seems to be kind of a Swiss Army knife kind of tip because of like the different things going on in it. But yeah, I have a bunch of soldering practice to do. I haven't gotten around to doing that yet. Um, I tried, I think the day before yesterday. I don't think it was yesterday. Or was it yesterday? No, maybe it was the day before. Or it could have been yesterday. I don't remember. No. I think it was the day before. Either way, I did try soldering practice, and it didn't really work out as well as I thought it would. And that is telling me that I definitely need to do a lot more practice. I probably shouldn't try directly soldering onto a potentiometer. I think I should spend some time just soldering onto perf boards and soldering wires, soldering single core wires and copper wires. I feel like with copper wires, I would have a much better time because when you talk about a copper wire, a lot of times it's not single core. A lot of times, even the thinnest copper wire that you get, internally, it's going to have very thin copper strands. So, like the copper wire itself is a bunch of copper strands that have insulation around them. The insulation is just the coating of the wire. So a lot of times the copper wire that you do get, it's going to contain these small copper strands, and it's essentially like when you strip it and then you tie two copper wires together, you're creating a weave sort of thing. I feel like the heat transfer in that kind of situation is much better than than like a single core or sorry, a single core wire which is not copper, or a potentiometer leg which is also not copper. I feel like the heat transfer when I'm doing it with copper wires is much better. And also, in terms of binding, assuming you've done the, hold on, give me a second. Yeah, assuming you've done, assuming you've gotten rid of the oxidation well enough, and assuming heat transfer has happened properly, it's assuming that. Give me a second. Okay, assuming heat is transferring well from the soldering iron to the wire, you won't have trouble in terms of getting the solder to bind to the wire, bind to the copper. And so it'll be much easier for you to actually get the solder to stick to the surface. But then with the single core wire, I've been having trouble getting the heat to transfer very well. Um, and also I've been having trouble getting the solder to stick on there. It has sort of a weird behavior when you try to get the when you try to melt the solder onto it. I still haven't figured out exactly why that is. Um, Another thing I need to look into is making sure the things that I'm soldering are stable, because I had this issue with the potentiometer as well. I had this issue with the single core wire as well when I was trying to solder the thing. Um, Sorry, when I was trying to tin it. So I was trying to apply a bit of solder onto the wire first, because generally what they recommend is you apply a bit of solder to the wire itself. So that's called tinning the wire, and then you also tin the, let's say you're soldering something to the potentiometer leg, right? You tin that leg as well. It's a tiny amount of solder, just enough to, you know, apply to the surface. And then you you touch both of these things together and heat both of them up together and use a little bit of more extra solder, and that's what creates this bind. Because now that you have solder on both of the surfaces, the heat transfer is going to be much better than it would be if it was like a if both the surfaces were bare. What was I saying? I was talking about I forgot why exactly I was talking about the tinning of the surface. Either way, I need to do more soldering practice, much more soldering practice, and I don't think I should try to solder anything onto anything until I've actually got it down to a proper workflow, and I should probably stick to just soldering with the perf board and the wires and stuff. Okay, so um, yeah, I guess let's just jump into the conversation that I was having with Gemini about potentiometers. Actually, give me a second. There's something else that I'm reading here. I'm just going to read that real quick, and then we'll continue. Just a second, or a couple more seconds. Hold on. Okay. All right. Sorry about that. I was looking into something. Um, okay. All right. Okay. So, we were looking into potentiometers, and I had a thing open. Understanding trimmer potentiometers. Okay. No, wait, that's a different thing. Understanding potentiometers. That's what I'm looking for. Okay, what is a potentiometer? At its simplest, a potentiometer or pot is a variable resistor. Inside the casing is a resistive track, usually made of carbon, and a sliding contact called a wiper. As you turn the knob, the wiper moves. Wait, hold on. As I'm reading this, I think because my fans are becoming loud, I think I'll just freeze the RTMP feed for a second, well, or for a couple of minutes just to bring the temp down a bit. It's gonna this is gonna freeze the. Actually, wait, this is interesting. It froze the kitty terminal that's being captured, but it didn't freeze the webcam feed. I thought it's gonna freeze the webcam feed as well, but that's OBS is directly interfacing with the webcam, whereas with the Kitty terminal, I have the Kitty terminal window, and that's being captured by OBS. So these two things are working differently. So okay, yeah, I guess that's good. Um, the feed is still being broadcast, or at least the camera feed is still being broadcast. Okay, so as you turn the knob, the wiper moves along that track. If the electricity has to travel through more of the track to get to the wiper, the resistance increases. If the path is shorter, the resistance decreases. Most pots have three pins. Pin 1 is the input, example 3.3 volts. Pin 2, um, which is the middle pin, is the wiper, and it's also considered the output. And pin 3 is ground, which is 0 volts. Okay, the voltage divider concept. You mentioned a voltage divider. This is the quote unquote secret sauce of how a potentiometer works with a microcontroller. A microcontroller, like the ESP32, doesn't generally feel resistance directly. However, it can measure voltage using its ADC. Um, using its ADC. A voltage divider turns a change into resistance. Wait. Oh, a voltage divider turns a change in resistance into a change in voltage. All right. Okay. Imagine two resistors in series. If they're equal, the voltage exactly in the middle of them will be half of the total voltage if you change. Hold on. Imagine two resistors in series. If they are equal, the voltage exactly in the middle of them will be half of the total. Okay? If you change the ratio of those two resistors, the voltage in the middle shifts up or down. So to calculate that, we use Vin um, multiplied by R2 divided by R1 plus R2. Okay. In a potentiometer, the two resistors, quote unquote, are actually just two sides of the resistive track divided by the wiper. Okay. Um, Divided by the wiper, by turning the knob, you are manually changing the ratio of R1 and R2. Okay, how your ESP32 sees it. When you connect pin 1 to 3.3 volts, pin 3 to ground, and pin 2 to GPIO4, when the potentiometer is turned all the way left, pin 2 is touching the side connected to ground, and your ESP32 reads 0. When it's turned all the way right, pin 2 is touching the side connected to 3.3 volts, and your ESP32 reads 3.3 volts. In the middle, you get roughly 1.65 volts. In your no STD Rust code, you'll use ESP32 HAL or ESP HAL. In my case, it's ESP HAL. Actually, I think in general it's ESP HAL. To configure GPIO4 as an ADC pin, the ADC will convert that 0.3 0 volts to 0.3. My God. The ADC will convert that 0 volt to 3.3 volt range into a number which is usually 0 to 495, sorry, 4095 for a 12-bit ADC. Okay, so this gives us, I'm assuming, an unsigned integer because it says 12 bits, but then I'm not seeing any decimals. So I'm guessing it usually gives us, and I'm also guessing this is where the resolution comes in, because there was a thread about, um, hold on, let me come here. They even mentioned it here. Um, in, I think it was in the read function. Give me a second here. I need to find the thing. Okay, let's look here. Read one shot. Actually, I think it might have been mentioned here. ADC calibration is not implemented for all targets, and it turns out for ESP32, it has not been implemented so far. They have a list over here. Okay, okay. Are we good? I hope it comes back, dude. Yes, yes. Okay. We are good. So maybe in the future I should just start doing this. The moment OBS just kind of disconnects, at least in this situation, I had control of the UI, so that was I guess lucky for me. In other situations, it usually freezes. OBS usually freezes. But yeah, okay. At least in this case, we didn't have to restart the stream. We do seem to be dropping frames, so I need to pause. I need to do a couple of things to reduce the load on the connection. So just hold on. Okay, I think we should be good now. Yeah, I think we should be good. Oh, dude. Okay, I do not have stream quality options, and for some reason I seem to be streaming at 1080p. I didn't know I stream at 1080p. I thought I stream at 720. Yeah, no, I'm pretty sure I stream at 720. Oh God, I shouldn't have done that. Okay, well, I did it. No, yeah, it's outputting at 720 after scaling it down from 1080, which is what I capture the thing at. I should look into whether this is a bad thing, because the reason I stream at 720 and not 1080 is solely um because of my internet connection, because I'm trying to not put as much of a load on the connection. I don't know if that's somehow putting a load on the system, because the system has to or OBS has to scale the resolution down and then stream it. And here it's saying 1080, so I'm wondering if Twitch is then scaling it up. Hold on, let me open up my stream separately, or let me open up my stream as the actual stream and not in my stream manager. Yeah, it says 1080p source. So I think Twitch is scaling it up. So I guess I have to just keep an eye on OBS the entire time. You know what else I could do? So I was planning on creating a simple sort of controller application that would use one of the OBS WebSocket libraries. I was planning on creating this in Rust, and mainly I was going to use it as a remote control to allow me to um, turn certain sources in a scene on and off, and maybe also switch scenes if I need to, like maybe switch from the current scene to like a BRB screen. Hold on. Yeah. So what I'm thinking is, if I'm pretty sure the OBS WebSocket API is gonna give us an option to poll to check if we are currently live or not. And I'm pretty sure it's also going to give me this information, basically stats related information, because like right now in OBS I'm able to see um, a section called dropped frames, for example. That's how I know how many frames I've dropped throughout this entire session, right? So if I ever get the doubt that OBS is not live anymore, or if I get the doubt that I'm having a whole bunch of dropped frames, I want to be able to visualize that in a separate application on a separate machine. Though I'll have to write that application. I'm not yet very good with Ratatouille, which reminds me, I do need to continue learning about Ratatouille as well. Though on the bright side, at least we are making progress on this front. So I'm not complaining. As an added bonus, at a later time, I could, like, whenever I do learn Ratatouille and whenever I've um, managed to interface between my ESP32 and one of the TFT displays that I have, eventually I could use what do I even call this? Not It's not a Ratatouille port exactly, but it's a crate that allows you to use Ratatouille to build TUIs for microcontrollers. So basically, it allows you to use Ratatouille with embedded graphics, and because it's using embedded graphics, that's why you're able to use it with microcontrollers. So you can use this library is called Mouse Food. I don't remember if I mentioned it. The library is called Mouse Food. Using that library, you can build TUIs for your your TFT displays, and I do intend on using that library at some point later on, because I did have ideas for being able to create various types of, not exactly graphical applications, but like the applications would require some kind of UI, right? I would prefer for there to be a terminal based UI, or at least something that has TUI that has a TUI aesthetic. Because in this case, I don't think it's necessarily going to be terminal, because it's not writing to a terminal. I think it's using Ratatouille's methods of drawing, and it's then applying those methods to something like embedded graphics, and through that, it's then able to draw directly onto the TFT display, meaning there is no terminal in between. Though I should check, because like what if it's really introducing a terminal first and then drawing? I don't think that's the case though. I think it's just using Ratatouille's ways of drawing TUI to then draw TUI directly onto like a screen buffer kind of thing. All right, give me a second. Okay, right. Let's continue. Oh yeah, I need to switch back here so now you guys can now the matrix rain is working as well. Let me make sure we don't have too much lag. Okay, it's like a 2 second lag, 1 2 second latency. We can. Oh yeah, I had to ask Gemini this question. Hey, I'm doing no STD. I'm learning. No STD Rust for ESP32 development. I want to use the ADC on the ESP32. However, the crate mentions something very specific. I want to get that wording right. Okay, however, the ESP HAL. Oh, okay. Yeah, never mind. The ESP HAL docs mention mention that the implementation state for no, no, mentions docs mention that ADC calibration is not implemented for all targets. They've given a link to the GitHub issue tracking this, and in that issue, wait, are we dropping frames again? We were dropping frames. However, we are still live. Okay. Oh, just a second here. Turns out there are a couple of things that I could do to improve the bandwidth a bit. Yeah, I think we should be doing a bit better now. And in that issue, they've mentioned a couple of ESP32 models. The one I'm using, ESP32, is apparently not implemented. There you go. I'm wondering what this means in terms of me being able to use the ADC. It's a bit of a good news, bad news situation. The short answer is yes, you can absolutely still use the ADC, but your readings will be physically off unless you do some heavy lifting yourself. Unless you do some of the heavy lifting yourself. In the world of no STD Rust on ESP32, calibration not implemented usually refers to the HAL, hardware abstraction layer, not automatically applying the factory burned calibration values to your raw digital readings. I'm guessing this is why, and holy shit, this is like some, I guess the best term for this is foresight. Like, in another conversation, I'd asked Gemini to generate a syllabus for me where Gemini teaches me analog electronics through the use of microcontrollers specifically, right? And Gemini had this idea because like I was constantly running that same prompt through Gemini, getting Gemini itself to refine the prompt for me. And Gemini kept pointing out that, hey, this might be an issue, that might be an issue. You might need to include this and that and this and that, and certain assumptions and stuff like that. Certain things I thought of from my side as well. There were certain things that Gemini mentioned that I felt would be better worded in a different way. And so I worded them in a different way and added them to the prompt. One of the things that Gemini mentioned, and that's actually in like, I believe the first or second chapter, we begin by calibrating the ADC. We literally begin our practical stuff by calibrating the ADC. This is something that I wouldn't have even thought about unless Gemini had mentioned it. And like here we have already run into this issue. Though the good news is that it's implemented for the majority of the other ESP32s. There's like, I don't know, 10 models listed there. Sorry, 7. There's 7 models listed here, and for 5 of them, it's already implemented. Okay, going back to this. So, what this means for your project, when you read a value, hold on. In terms of calibration, Wouldn't this just mean that I need to test out min and max values myself? Like hook up a potentiometer to VCC and ground, and the middle pin goes to ADC, and then I take it all, I turn the potentiometer all the way to one side and note down the value there, and then turn it all the way to the other side and note down the value there. And the shortest of those values, the smallest of those values is the minimum value, and the largest is the maximum value. And that's our range, essentially. Like, is there anything more that needs to be done in terms of calibration? Because like in that way, I guess I can kind of determine the bit depth of it as well. Yeah, I probably won't have, you know, something, I won't have it like written down somewhere that, oh yeah, this is definitely what the bit depth is going to be. This is definitely what the resolution is going to be. But I can calibrate it myself. I'm assuming that that's what I need to do, right? I need to calibrate the thing myself, and then I can use it. Okay, so let's see what Gemini is saying. When you read a value from an ADC, the chip converts a voltage into a number, which is 0 to 490 to 4095 for a 12-bit ADC. Ideally, 0 volts would always be 0, and 3.3 volts would always be 4095, but silicone isn't perfect. Okay, two types of errors. Without calibration, you will encounter two main issues. Offset error, when you have zero volts on the pin, the ADC might report 50 instead of 0. And gain error, the slope of the conversion is slightly tilted, meaning 1 volt might look like 1.05 volts on one chip and 0.95 volts on another chip. Okay, that's crazy. The ESP32 specific quirk. The original ESP32, the non-SC variants, okay, so the one that I'm using, is notorious for having a non-linear ADC response, especially at a very low and very high, especially at the very low and very high ends of the voltage range, near 0 volts and near the reference voltage. Note, most ESP32 chips have ADC calibration values burnt into their eFuse memory at the factory. When the HAL says it's not implemented, it just means the software hasn't been written yet to grab those specific eFuse bits and apply the math to your ADC.read results automatically. Your options right now, if you need to move forward, you have three paths. One, ignore it. The accuracy will be low. It's fine for is the battery low or is the light on? And then there's manual offset. The effort is low and the accuracy is medium. So measure 0 volts, subtract that constant from all the readings. Measure 0 volts. Oh, measure the ADC reading at 0 volts. So we calculate what the offset would be, and then we basically do that offset ourselves. Earlier when Gemini was mentioning this thing about calibration, I didn't realize it was this. I thought it was more about like what specific range it maps to. Technically, that could still be true. Yeah, that could still be true. Yeah. I think that could still be true. Like maybe some microcontrollers don't use 0 to um 4095 range, as in maybe some microcontrollers don't use uh a 12-bit value. Maybe they use lesser, maybe they use more. I don't know. Okay, then we have 2-point calibration. The effort is medium, but the accuracy is high. So you measure two known voltages and calculate your own y equals mx plus b. So you plot your own line for this. But isn't it? Didn't you mention earlier that it's non-linear? Yeah. Okay. The original ESP32 is notorious for having a non-linear ADC response. But then y equals mx plus b. This is interesting. I'm definitely curious about how this would be working exactly. Yeah, yeah, I'm curious about how this would be working. I also want to go look at all my other ESP32s and check if by chance I happen to have any ESP32 C3s or S3s that are on the bigger side and have pins soldered to them. The bigger ones will definitely have pins soldered to them. Most of the bigger ones that I ordered, they came with the headers soldered. Okay, a quick tip for better accuracy. Even without software calibration, you can significantly improve your results by using multi-sampling. Since the ESP32 ADC is a bit noisy, taking 10 to 20 readings in a row and averaging them will give you a much more stable, though still calibrated value. Okay, that's a good, true, yeah, okay. Multi-sampling. That's a good idea. I should keep that in mind. It's gonna it's gonna be slightly heavier, but I mean, so far I'm doing very lightweight stuff. I'm not doing anything that's nearly close to, the maximum ESP32 hardware capability. So I don't think I need to worry about that. I don't think I need to worry about that for now. Okay. All right. Hey, wait. I'm confused about that y equals mx plus b thing you mentioned. Explain to me how that is meant to be working. Isn't that the formula to plot a line? You've got it exactly right. That is the formula for a straight line. We use it, the reason we use it for an ADC is that in an ideal world, the relationship between voltage or input and the digital number is a perfectly straight line. Okay, in an ideal world. When the HAL says calibration is not implemented, it means the chip doesn't know its own specific line yet. Why the line matters: think of the ADC as a machine that translates X volts into Y digital units. That makes sense. M is the slope. This represents the gain. If the slope is too steep, your readings will rise faster. Okay, that makes sense. Yeah, yeah, that makes sense. If the slope is too steep, then a short increase in the voltage would give you a very high increase in the reading. So a short increase in the analog voltage would give you a very high digital reading. Uh, then B is the y-intercept. This is the offset. If B is not 0, your ADC will say 50 even when the pin is connected to ground. Okay, how you quote unquote calibrate with this formula. Since the ESP32 doesn't do this for you in no STD yet, you can create your own quote unquote map using a multimeter and two data points. Point A, you connect the pin to ground and then read the ADC. Let's say it returns 42. Connect the pin to ground. Connect the pin of what? The multimeter? Okay, fine. Let's look at point B. Connect the pin to a known 1 volt source and then read the ADC, let's say 1242. Now that you have two coordinates, you should be able to calculate I'm assuming now that you have it, you should be able to calculate the slope and maybe the intercept as well. I think so. Now that you have two coordinates on a graph, you can now calculate M and B to fix every future reading. Okay, so M, this is interesting. So M would be, okay, wait. So, so the way that they are telling us that we can calculate M here is doing 1242 minus 42. 1242 minus 42 divided by 1.0 minus 0. So basically we are taking the 2 points from, or the two components from point A, which is our ground voltage, and the corresponding digital reading, and point B, which the 2 points are our 1.0 volt source and the corresponding digital reading, which is 1242. And then we are creating a formula out of that. So then M there turns out to be 1200, and B, since at 0 volts the output was 42, B would be uh, B would be 42. That's interesting. I feel like there's something to be explored here. Yeah, I feel like there's something to be explored here. Because I feel like this exact method can be used to um, develop a sort of linear formula for other situations. Yeah, okay, hold on. I'm going to continue reading this. Voltage equals raw reading minus B divided by M. Now, every time you take a raw reading from the ADC, you just reverse the math to find the actual voltage. Okay, hold up. You know what? Okay, so the ADC is not, it's not calibrated, right? Does that mean that anything harmful can happen? I think that just means that we'll get slightly inaccurate readings. But I think for the purpose of being able to just read analog stuff, I think we should be good. Like slightly inaccurate readings is not so bad, as long as we have like, an entire range that seems to be very visibly changing. Because if we are talking about like a 12-bit range, if we are talking about 4096 possible values, then I think throughout that entire rotation of the potentiometer, we are going to see the values increasing and decreasing. So I think in terms of calibration, I should be fine. Let me ask Gemini this. Okay, one catch. The original ESP32 is ESP32 ADC is mostly a straight line, but it flattens out at the very bottom near 0 volts. Wait, it flattens out at the very bottom near 0 volts and at the very top near so and so. This is called nonlinearity. If you try to measure 0.05 volts, the formula might stay at 0 volts because the ADC hasn't woken up yet. Okay, for the best results, with your manual MX plus B math, try to stay in the sweet spot between 0.2 volts and 2.5 volts. Okay, couple of things. The way that you have applied this y equals mx plus b formula and how you derived m and b seems really interesting because I feel like this concept could be applied in other situations too. Let's dive into that. Okay, so now that I know my ESP32's ADC is probably not calibrated, if I'm mainly learning things right now and don't require the utmost accuracy, how good or bad of a learning experience would I have if I didn't bother calibrating and just used the ADC as is? Because this is what I'm wondering. Like, do I need to calibrate it if I'm not doing highly accurate stuff right now? Do I need to worry about the accuracy? Okay. Yeah, sorry, zoned out. You're touching on a fundamental concept in engineering. That y equals mx plus b approach isn't just for ADCs, it's the basis for linear regression and sensor fusion. Linear regression, yes, definitely, I've seen it being applied there. That's exactly how we calculate, um, that's exactly how we apply um, the linear regression method once. How, what am I trying to say here? That's exactly how we use linear regression to predict new values once we have calculated the weights essentially uh, using something like ordinary least squares method. Once we calculate that, what's returned to us is m and b. So we can then construct our straight line, and given any x value, we can plot y very easily. Okay, let's break down your 2 points, the magic of the formula and what your learning experience will actually look like if you ignore it for now. Now, I'm not going to touch the formula just yet. This, I'm going to do it off stream. I'm going to continue now with this thing. Learning without calibration, is it worth it? If you choose to ignore the calculation, if you calibration, not calculation, If you choose to ignore calibration right now, your learning experience will be mostly unaffected, provided you keep a few things in mind. The quote unquote good part of the experience, logic remains the same. The code you write to initialize the ADC, select a channel, and trigger a read is identical whether your chip is calibrated or not. Okay, give me a second here. Okay, all right. Whether your chip is calibrated or not. Oh, you know what? I can bring this back. Uh, Whether the chip is calibrated or not. Relative changes still work. If you turn a potentiometer, the numbers will go up. If you put a light sensor in a dark room, the numbers will go down. Okay, good to know. For learning how to use a peripheral, this is 100% sufficient. Then the frustrating part, which is the lying multimeter. If you use a multimeter to check the battery and it says 3.3 volts, but your ESP32 says 2.9 volts, you might spend an hour debugging your code thinking you have a bug. The bug is just the uncalibrated hardware. Okay, good to know. This actually might become important when I'm actually using this as a multimeter or as a voltmeter, because I just remembered the reason we had to do the calibration was because um, the we were planning on using the ESP32 as a as a voltmeter as well. Yeah, that's why we were doing the calibration. I just remembered that. Okay, dead zones. On the original ESP32, the ADC is quote unquote blind below zero point 0.1 volts. You might connect a pin to a very weak signal and get zero back, leading you to thinking your wire is broken. Verdict: if you are just learning how to write no STD Rust, skip the calibration for now. Focus on the HAL, the registers, and the async slash interrupt flow. Just keep a mental offset that your numbers are ballpark figures, not scientific measurements. Okay, another thing about the ADC are the values always 12-bit, so 0 to 4095, or can I expect other ranges as well? On the original ESP32, the hardware is natively 12-bit, meaning the internal successive approximation register breaks the voltage into 2 to the power 12, so 4096 steps. However, in practice, you will encounter two different ranges depending on how you configure your code. Configurable bit width. The ESP32 allows you to downsample the resolution. Okay, all right. So you can do 12-bit. Oh, in most Rust ESP HAL um, implementations, you can set the bit width to 12-bit, 11-bit, 10-bit, and 9-bit. Okay, so that would be 1496, 2048, 1024, and 512 respectively. Why would you want fewer bits? Lower resolution can sometimes be slightly faster to read, and it naturally acts as a filter for tiny amounts of electrical noise. If you only care about whether a dial is at low, medium, or high, then 9-bit is much easier to handle than 12-bit. True, true. The effective range. Wait, okay, so the range, what I'm getting here is that the range would be 12-bit, but you can configure it to be lower. Wait, so am I? Oh, okay. Summary for your learning. The output value is usually 12-bit. unless you manually change the bit width, and the voltage input is usually 0 volts to 2.5 volts. If you try to measure 3.3, if you try to measure the 3.3 rail directly, you'll notice the value stays at 1495 for a large chunk of the upper voltage range. This is called saturation. Okay, good to know. Good to know. So now we are going back to potentiometers. Yes, so this is where we had come to the question about calibration. So in here, it mentions that when you connect pin 1 to 3.3 volts, pin 3 to ground, and pin 2 to GPIO 4, then you get these different values at different stages. In your no STD Rust code, you'll use the ESP32 HAL or ESP HAL to configure so-and-so. The ADC will convert that 0 volt to 3.3 volt range into a number, usually so-and-so. Why the resistor and LED? You mentioned having an LED and a resistor in the mix. Usually in a beginner setup, there are two ways to use this. Analog input, you use the pot to tell the ESP32 a value like a volume knob, then use the ESP32 to dim the LED using PWM. And another is current limiting. If you were using the pot directly with the LED, no ESP32 involved, the extra resistor is a safety net. Yeah, that's true. I do have that extra resistor even now. So when even when I've turned the trim pot all the way down, the LED isn't completely bright because there's a tiny bit of resistance in there. About probably 270 ohms of resistance is still in there. Also, I'm not entirely sure if the pot's zero resistance is actually zero resistance. I feel like I should look into that. Like, is there still like a small amount of resistance being applied there? But okay. Um, Current limiting. Potentiometers can sometimes be turned into zero resistance without a fixed resistor. In the series, the LED would receive too much current and burn out instantly. Note, for your ESP32, make sure you are powering the pot with 3.3 volts, not 5 volts. The ESP, oh shit, I need to be careful of that, yeah. I also need to check, I need to check that, hold on, wait. I need to check if I even have access to 3.3 volts on this side because I don't have access to, hold on just a second. Well, okay, I can say it without having to point at it. I don't have access to the other side. I don't have access to the other side of the ESP32, so I can't do anything with the pins on that side. Yeah. So like I was saying, I don't have access to, wait, are you guys able to see this? I hope so. Yeah, I don't have access to pins on this side. I only have access to pins on this side. Yeah. Okay. So that's working. Great. Awesome. Okay, there was another question that I wanted to ask. I want to dive deeper into the voltage divider thing. Hey, so before I proceed, I do want to dive deeper into the whole voltage divider thing because I because so far all I understand is connect pin 1 to VCC, pin 2 to ADC, and pin 3 to GND, but I don't fully really understand what's going on there. I don't understand at what point the voltage is what and the current is what, which is kind of true. Um, I, I, I want to get a better understanding of how exactly I'm meant to be using a voltage divider. Um, this is a what 10K ohm potentiometer. So what I could do is I could I could use wait, if this is a 10K ohm potentiometer and the voltage divider halves the voltage, doesn't that mean we are... No, it halves the voltage. But okay, if we are talking about, if we are looking at it in terms of ratio, doesn't that mean that we are dividing it into 5,000 and 5,000 ohms, so 5K and 5K? See, this is why I'm confused about this, because like, how am I meant to be thinking about this? Okay, let's see what Gemini is saying. To understand the voltage divider, we have to look at how voltage drops across resistance. Think of voltage like water pressure and resistance like a narrow pipe. When electricity flows through a resistor, it uses up some of its pressure, which is voltage. Hold on. When electricity flows through a resistor, okay, it uses up some of its pressure, which is voltage, to push through. By the time it exits the resistor, the pressure is lower. All right. The fixed voltage divider. Imagine two equal resistors, 10K each, connected in a row, as in series, from 3.3 volts to ground. All right. At the top, which is VCC, the pressure is 3.3 volts. The first resistor, um, the current has to fight through this. Since R1 and R2 are equal, the electricity spends exactly half of its energy here. The middle point, which is the quote unquote tap or faucet, if you stick a multimeter probe here, you will see 1.65 volts. The voltage has divided based on the ratio between the two resistors. The second resistor, which is R2, the remaining 1.65 volts is used up pushing through this last stretch to reach ground. So the remaining voltage is used up pushing through this last stretch to reach ground. Okay. The potentiometer as a sliding tap. Uh, a potentiometer is just those two resistors, but the middle point can move. Inside the pot, you have one long track of resistive material. The total resistance, let's say 10K ohms, never changes between pin 1 and 3. However, your wiper slides along that track. Your wiper is pin 2. turned to one side, the wiper is physically touching pin 1. There is zero resistance between the input and the wiper. So the output there would be 3.3 volts. And if it's turned all the way to the other side, the wiper is touching pin 3. Wait, that's interesting. Yeah, I just realized that now we have 3 pins. Now it's not just 2. So then it's then I think it's the, what do you call it? The microcontroller that's measuring this thing, using both of them as a reference, using pin 1 and 2. No, sorry, pin 1 and 3. So using its VCC and ground as a reference to calculate what the wiper is doing. Hold on. Let's continue reading. Okay, anywhere in between, you are essentially creating two resistors. R1 is the distance from pin 1 to the wiper. R2 is the distance from wiper to pin 3. What about current? This is a crucial point for hobby electronics. A voltage divider is for signals, not for power. Because the ESP32 ADC pin has high impedance, meaning it's like a very, very tiny straw. It draws almost zero current. It just looks at the voltage level. So the current equals voltage divided by resistance. If you have a 10K pot on 3.3 volts, the current flowing through the pot itself is 3.3 volts divided by 10K, which is 0.33 milliamps. Wait, 0.33 milliamps. To light up an LED, you need around, or well, the usual operating voltage for one of these LEDs is usually around like 10 to 20 milliamps. That's more on like the lower range as well. And here they're saying 0.33 milliamps. So this is a tiny safe amount of current that just sits there creating the voltage map for your ESP32 to read. Why don't we use this to power an LED? You might think, can a voltage divider give my LED exactly 2 volts? The answer is usually no. If you connect a load like an LED to the middle of the voltage divider, the LED acts like a third resistor in parallel with R2. This changes the total resistance of the bottom half, which messes up the math and drops the voltage further than you intended. The golden rule: use voltage dividers to tell a microcontroller what a knob position is. Use PWM or a dedicated regulator to actually change the power going to a component. So what I'm getting here is that the voltage divider is mainly meant to signal something here, but like, let's say we are at hold on, I need to open up a Python thing. Do I still have the Python thing open? No. Okay. So let's say 3.3 K divided by 10K. That's our milliamps. That's 0.33 milliamps. Right now it's 0.00033 amps. Great. Okay. If we are halfway through, or let's say 1/4 way through, the resistance is very low. So what are we looking at there? Yeah, there we might be looking at, because, okay, what do we need to multiply this by 1,000? Yeah, we need to multiply this by 1,000. So it's 1.33 amps. No, 1.33 milliamps. Uh, okay, so I feel like I'm kind of getting it, but not fully getting it. Am I mainly supposed to be using voltage dividers in a MCU related circuit? Uh, because it seems like trying to actually use this for lowering voltage slash current doesn't always work out the way you think it would in a analog circuit. You've hit on the single most important moment in hobby electronics. Man, this Gemini really exaggerates about things sometimes. Anyways, okay. You are exactly right. A voltage divider is for information, not for power. In the world of microcontrollers, we use them almost exclusively as sensors. The loading problem, why it fails for power. The reason a voltage divider doesn't work for powering things like a motor or a bright LED is that uh, is that the device you attach becomes part of the math. Imagine your divider is two 10K ohm resistors giving you 1.65 volts. Okay, so at the center is giving 1.65 volts. If you attach an LED that also has some internal resistance, you have now placed the LED in parallel with the bottom resistor. Suddenly, the bottom half of your divider has much more resistance than 10K. According to the voltage divider formula, V in multiplied by so and so. If R2 gets smaller than V out, no, if R2 gets smaller, then V out drops significantly. Your 1.65 volts might suddenly sag to zero point 0.5 volts, and your LED won't even turn on. Why this works for your ESP32? The ESP32's ADC pin is designed to have high input impedance. Think of the ADC like a person holding a voltmeter who is looking at the wire but not touching it heavily. It draws so little current, picoamps, that it doesn't load the circuit. Um, doesn't load the circuit. Okay. Because it doesn't draw current, the R1 and R2 ratio stays perfect and the voltage stays exactly where you calculated it. Common MCU use cases. Aside from reading a potentiometer, here's where you will see voltage dividers 99% of the time. Battery level monitoring. If you have a 7.4 volt LiPo battery, but your ESP32 can only handle 3.3 volts on its pins, you use a voltage divider to scale down the battery voltage so that the ESP32 can safely read it. Oh, read, not use. Okay, okay. Then resistive sensors. Components like photoresistors and thermistors change their resistance based on the environment. If you put them in a voltage divider circuit, so the MCU can see the environment change as a change in voltage. What? Oh, it's just saying you put them in, not if you put them in. Okay, you put them in a voltage divider circuit, so the MCU can see, quote unquote, the environmental change as a change in voltage. Then level shifting. If you have a sensor that talks at 5 volts, but your ESP32 is 3.3 volts, a divider can step down the signal pulse so you don't fry the ESP32. Summary: the golden rule. Voltage divider, use it to move signals or data. It tells the ESP32 what is happening. And voltage regulator slash transistor slash PWM, use these to move power. They do not heavily, they, no, they do the heavy lifting to actually make things happen. Okay. All right. Okay, so am I getting this right? Anytime I want to make a voltage, anytime I want to make a pin read voltage as a tiny signal, um, rather than something that's powering something over time, I connect, no, yeah, okay. I create a voltage divider using two resistors and basically just use different, basically just change the resistance ratio on each side to vary the signal. This is like a very convoluted example that I've given, but like basically what I'm saying is anytime I want to simulate a potentiometer, or even just feed a small signal in. I could have mentioned that. Yeah, I could have mentioned that. Okay, you've got it. This is the perfect mental model for how to use a voltage divider in the digital world. You are treating the resistors as a translator that turns a resistance value into a voltage language that the ESP32 can understand. To solidify this before you start writing your NoSTD code, your NoSTD Rust code, there are two tiny nuances that'll make you feel like a pro. The wiper is the magic shortcut. In your specific case with the potentiometer, you aren't physically grabbing two separate resistors. The potentiometer is the entire divider in one package. The top resistor is the track between pin 1 and the wiper, and the bottom resistor is the track between the wiper and the pin. When you turn the knob, you are mechanically shrinking one resistor while growing the other. The total resistance, which is R1 plus R2, stays the same, but the ratio shifts. The impedance handshake. Since you mentioned you're learning NoSTD Rust, you'll eventually run into the term input impedance. Think of think of the ESP32's ADC pin as a very high quality voltmeter. Wait, think of the ESP32's ADC pin as a very high quality voltmeter. It has such high resistance internally usually in the mega ohms range, that it doesn't steal any current from your divider. This is why your math stays clean. If the ADC had low, if the ADC pin had low resistance, it would leak current to the ground and your voltage signal would sag, giving you an inaccurate reading. Why this matters for your Rust code? Okay, yeah, that's fine. It's talking about like the ADC readings. Um, hey, so I'm confused about how um, there's no heating up or frying happening here when there's nothing consuming this voltage slash current. I guess, and this is true. I guess I don't fully understand how the ADC is really quote unquote reading the voltage or signal, and how 3.3, how VCC and GND being involved helps. Okay, this is a perfect question. It touches on the difference between a short circuit, which fries things, and a resistive circuit, which is what you have. The reason your components aren't melting is due to Ohm's law. V equals IR. Why it doesn't fry? The resistance buffer. If you took a plain wire and connected 3.3 volts directly to ground, the resistance would be almost zero. And according to I equals V divided by R, if R is nearly zero, the current becomes massive, and that is a short circuit, heat, sparks, and a dead ESP32. Okay? However, your potentiometer has a fixed resistance, usually 10K, between the 3.3 volts and ground pins, between VCC and ground. I equals so-and-so, so-and-so. Right, so this comes back to our 0.33 milliamps current. So that is a tiny amount of current. It's it's like a slightly leaky faucet rather than a fire hose. The resistive material in the pot is consuming, quote unquote, consuming that energy and dissipating it as a microscopic, unnoticeable amount of heat. Hey, Zainar, hello, hello. Welcome to the stream. How's it going? Yes, yes, we are back, and we also have BREADCAM now. We are now doing ESP32 electronics streams. It's going to be a mix of no STD Rust coding and also learning digital electronics and analog electronics concepts. I'm kind of like learning things bit by bit. Gotten into my um, I haven't gotten into my analog electronics course yet. I know very basic analog electronics. I don't know, like, there's still a lot that I have to learn, which is why I've designed this prompt for the analog electronics course. We're going to get to that at some point soon. For now, though, I want to start by trying to recreate, at least for in terms of digital electronics, I want to focus on being able to run no STD Rust on the ESP32 and actually doing things with it. I like the breadboard cam. How did Python with Polar's learning go? It went well. Yeah, I'd asked Gemini to set up some simple exercises for me. I still have to go back to that. I don't want to actually. I okay. So because I like Polars so much more than pandas, I do want to stick with that. I wanna finish learning the basics, and then actually start doing stuff with it. In this case, right now, the stuff that I want to do is it very heavily involves my content pipeline project for, auto clipping and analyzing a bunch of stuff from stream transcripts and doing a bunch of NLP stuff. There's going to be a whole lot of data storage, data handling that's required, and I would prefer to use polars instead of pandas for that. So I'm still planning on continuing with polars, and additionally, I want to keep doing polars related exercises that I'll ask Gemini to generate for me. This works out great because I ask Gemini to generate a data set for me. Usually, what it does is because I ask it to generate such a big data set, so it creates the Python code to generate that data set. So it'll give me the Python code and say that this is going to generate so and so data set with so and so columns and stuff like that. And then I run that so I can generate the data set on my side. Once I have the CSV file, and now within that same Gemini conversation, since I know that Gemini now knows what the data set is about, I tell Gemini, okay, now based on this and considering the knowledge that I currently possess about polars, generate these exercises for me so I can practice. Good time to brush up on databasing too. True, true, for sure. Now, where was I with this? Fixed resistance. So currently I'm trying to understand. Currently I'm trying to understand the concept of voltage dividers here, and more specifically, like how they work, in what situations I would be using them. For example, reading a signal versus actually powering something with them. And I'm trying to understand how we are able to connect VCC to ground and also have, a pin in between connected without frying anything. So I've just been reading up. I've been talking to Gemini about that, and Gemini is explaining this. Um, how the ADC reads, quote unquote, without consuming. Think of the ADC pin on your ESP32 as a pressure gauge on a water pipe. The pressure gauge doesn't doesn't need to let water flow through it to tell you how much pressure is in the pipe. It just feels the push. Inside the ESP32, the ADC has a tiny capacitor. When you connect it to the potentiometer's middle pin, a tiny bit of charge flows into that capacitor until the voltage matches the voltage at the wiper. Once the voltage matches, no, hold on, I didn't catch that. Tiny capacitor, when you connect it to the potentiometer's middle pin, a tiny bit of charge flows into the capacitor until the voltage matches the voltage at the wiper. Tiny bit of voltage flows into, okay, all right, okay. Once the voltages match, no more current flows into the ADC. The ESP then looks at the charge on that capacitor and converts it to a number. That is so interesting. I had no idea that this is how ADCs work. This is interesting. So if I'm understanding this correct, it's the ESP32 that's trying to charge, that's trying to charge up the capacitor to bring its charge up to whatever is matching the with the middle pin voltage. And once it hits that, it doesn't go any further. And then once it hits that and doesn't go any further, then the ESP32 reads the charge at the capacitor, which I should also look into how it's looking at or reading the charge. But yeah, it looks at that charge and then converts that to a number. That is interesting. Okay, why involve VCC and ground at all? You need VCC and ground to create a reference frame. Voltage isn't an absolute value. It's a difference between 2 points. That's why it's called potential difference. Okay, if you only connected the pot to 3.3 volts but not ground, the electricity would have nowhere to go. There would be no slope for the voltage to drop across, and the entire resistive track would just sit at 3.3 volts. Oh, you know what? I think that's why using only two, like for example, if I turn this right now, like you can see it's dimming and brightening or lighting up more right now. I'm not using the three um I'm not using all three legs. I'm only using I'm only using two of the legs. So pin 1 and pin 2. And so the current is actually going through it. The current is not going from VCC to ground. Actually, in this case, it's not even going from VCC. It's going from yeah, okay, this raises a good question. If I were trying to power an LED with this, is there a situation where I would ever need to use the third leg of the potentiometer? Um, oh, also, I just noticed the time. I do need to end the stream right now. I wish I could stream longer. I just wasn't able to get the stream started up in time. I was busy with other stuff. I'll try to I'll try to start the stream earlier tomorrow. Again, we're going to be doing more electronic stuff. I'm excited. I'm excited that we're finally able to do electronic stuff on stream. Um, so yeah, I'm going to continue this research off stream because now I want to understand this. I don't want to let this thing go. That being said, Zainab, thank you very much for stopping by and chatting and hanging out. Anyone else who might have been lurking in the chat, thanks for hanging out. Um, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time.